Okay, so welcome back. The intention of this video is to show the meaning of those different terms on top of the ideal gas properties of any ideal gas. Not only of air, can be nitrogen or can be any other ideal gas. So you're familiar with the temperature, with the enthalpy, and with internal energy. But what about that P sub R, that V sub R? I think this one we already defined it, but probably we can redefine it in this video as upper sub O. So that's not really the total change in the entropy. Okay, so in order to do that, let me zoom out. All right, so let's recalling the equation for the change in entropy we had one expression that is of this form over here. If we are integrating here between, let's say, T1 and T2. This is the term that on a previous video, and this is because Cp is not constant, depends on the temperature. So this term over here, which is equal to S sub O T2 minus S sub O T1. Okay, so this term over here is the meaning of the term in the last column. Okay, I think this is more clear. Now let's see what is the term, the P sub R. Okay, so basically we do this, we can say that then the change in entropy is equal to what? S of CO2 minus S T1 minus R log P2 over P1. So this is what we know. So now for an isentropic process or cycle, but let's say process, what does that mean? That a total change in entropy will be equal to 0. So basically we can say that 0 will be equal to S T2 S T1 minus R log P2 over P1. Now we can just rearrange the equation as R log P2 over P1 will be equal to ST2 minus ST1, or log P2 over P1 ST2 minus ST1 divided by R. So now if we take the exponential function on both sides, what are we going to get? We're going to get that P2 over P1 will be equal to the exponential function of over R. Okay? Or using now the property that E of AB equal A E of B, we can write this as P2 equal to P1 exponential S0 T2 over R Okay, I should have put the divide sign after the parentheses divided by exponential S sub 0 T1 divided by R, like I did over here. Okay, so this is not that important, but what's important here to notice that this term over here, since R is constant, will only be in function of the temperature. So this term over here that you see is actually what they call P sub R. So this would be PR sub 2 over PR sub 1. Okay, so all this term over here is what is, or exponential of S divided by R is the PR. So from this equation, basically we have the relation that for an isentropic process, we're going to have the relation P2 over P1 equal PR2 over PR1. So this equation is valid for an ideal gas and for an isentropic process. Okay, so basically over here, now we know the meaning of the P sub R in the column. We need to do the V sub R, and this is now pretty simple once we have done this. Okay, so this is true for an ideal gas. So for an ideal gas, we know that PV equal RT. So from here we know that V will be equal to RT divided by P. Okay, so using this condition, we could rewrite that V2 over V1 will be equal to what? R T2 over P2 divided by R T1 over P1. So the R would cancel, and we are left over with what? T2 over T1 times P1 over P2. Okay, but recalling the previous equation, which is P2 over P1 equal PR2 over PR1, I can rewrite this as equal T2 over T1 times PR1 over PR2. And again, what happened is that you see that all this term over here, well, if you want to look at all this term over here, only depends on temperature. And basically, you can just rewrite it as V2 over V1 will be equal to VR2 over VR1. Okay, so we have also this relation. Again, this is valid for an ideal gas undergoing an isentropic process. So if we summarize, if you have an isentropic process and an ideal gas, these two relations here can be used. P2 over P1 equal PR2 over PR1, and V2 over V1, VR2, VR1. So why do we need that? Okay, so in most problems, if you remember from other problems, we need to find efficiency. So let's say you know the actual efficiency or the actual work created by a system, and you want to know what would be the ideal case. So you need to know what would be the isentropic. Okay, so then you can use these values here, the P sub R, to relate it to the actual pressures P2 and P1, or to relate it to the actual volumes. Okay, but I think probably the easiest is just to do an example. So again, remember in this video we look at P sub R, V sub R, and we redefine again the S upper sum knot. Thank you for your attention.